For my approval into, thanks the organizers for the invitation and what's turning out to be a great workshop. You've all probably seen this before. I couldn't resist putting it there just to bug Tom Killian because he's tired of seeing it too, even though he uses it as well. But basically the idea is plasma is interesting because it spans enormous orders of magnitude in temperature and density. And what we're going to be talking about with ultracold plasmas sort of goes off the standard chart of plasma physics. So temperatures down to, for electrons, down to below a Kelvin and this sort of density range. And one of the interesting things is it straddles the range to what's known as strongly coupled plasmas. So I'll talk today mainly about Rydbergs and ultracold plasmas. As we've heard already from earlier talks, cold Rydberg gases form ultracold plasmas. I won't talk about that except to show one short thing. Mainly I'm going to be talking about the importance of Rydberg atoms that are formed due to three-body recombination and their effects on the dynamics of plasmas and a little bit of the Rydberg physics itself. It's important because three-body recombination is, first of all, a LOX mechanism for the ultracold plasmas. It's also a heating mechanism. It's a very significant heating mechanism, which really, to a large extent, determines the temperature evolution in these plasmas we make. So that also affects the dynamics. And as we'll hear later from Jerry, if he's in here somewhere, understanding three-body recombination can be, can be critical for antihydrogen experiments. So to make an ultracold plasma, it's quite straightforward. Take a laser-cooled sample of atoms. In our case, we happen, for historical reasons, to use metastable xenon. We do a two-photon transition where the upper photon is a pulsed laser using kind of 1970s, 1980s era pulse dye lasers just to excite and ionize the cold atoms to slightly above the ionization limit. And because we start with a sample of atoms that's at 20 microkelvin, there's essentially no thermal energy available, so the energy we give to the electrons is just the difference in the photon energy minus the ionization limit. And so we typically do things in the of order 1 to 1,000 Kelvin region here. For pretty much all the data I'll show you today, it's a standard so this is a rather standard magneto-optical trap system, but we have it surrounded by grids, so we can apply electric fields, we can apply DC fields, we can apply RF fields, microwave fields, and then we detect charged particles, so we have some grids down below where we can accelerate either electrons or ions onto a microchannel plate detector, which is backed by a phosphor screen, so we can actually take images of the charged particle distribution as well. So here's a typical ultracold plasma signal. This is looking at the electrons coming off the system. We've tuned the electric field in the chamber to be on the order of 10 millivolts per centimeter, which is about as low as we can get. And what you see coming out, so we hit the atoms with a photoionizing pulse, and you see some prompt photoionization. And then over time, the electrons dribble out over a couple hundred microseconds. And so we form the ultracold plasma essentially immediately. And then as time goes on, as I'll talk a little bit, the plasma expands. As it expands, the confining potentials that are holding the electrons in the plasma are getting weaker and weaker, and the electrons evaporate out of the plasma. And so this is a single shot of data. We can get one of these once per second if we choose. And in fact, the way we tune those electric fields is by maximizing the duration of this plasma, because if you have an electric field on, that'll tilt the Coulomb potential and it won't last as long. And so this is a fairly sensitive way to tune up the electric fields. Typical parameters, the ion temperatures are quite a bit lower from kinetics, at least the initial ion temperatures, so they can still be in the millikelvin regime. Electron temperatures up to 1,000 Kelvin. Densities of order 10 to the 9, sizes 300 microns for a typical MOT we use. And it's a plasma because the Debye length, which to remind you is the screening length, is much shorter than the size of the system. So if I apply an external electric field, the charged particles rearrange themselves to screen it out. And that's true even as the plasma expands. It gets larger, but the Debye length gets larger, but they always, through the whole lifetime of the plasma, even when the density is down by 5 orders of magnitude, the Debye length is considerably smaller than the size of the plasma. One thing I just wanted to mention, if you look at this plot, I said this was evaporation. So coming from a BEC background, I'm used to forced RF evaporation, nice thermal equilibrium, and the like. If you have a finite potential well, you can't, strictly speaking, have a Boltzmann distribution because it doesn't integrate up properly. So it has to have some variation at high energies. Now the electrons, if you look at the classical collision cross sections, it's very fast for these cold electrons. So the electrons are in good quasi-thermal equilibrium with each other. They're distributing their energy very rapidly compared to the lifetime of the plasma. But there's an interesting question as to what's the real distribution. So it's probably very Boltzmann-like for most of it. And what happens at the high energy tail? So various theoretical models that have been used have used the simplest thing, which is just truncate the Boltzmann distribution, or actually another model which actually comes out of galactic cluster physics is known as the Michie-King distribution, which is essentially just take a Boltzmann distribution and offset it vertically, and when it crosses zero, you stop it, kind of thing. And there have been a few experiments trying to probe these differences, but they're rather subtle. But I think it's an interesting problem, which we really haven't addressed. And just to point this out, we can skip that, just to show you that there's, I think, some interesting physics here. Here's a simple experiment we did. The black curve is our usual plasma curve. And at various times in here, we just turned on a pulse of a DC electric field for a microsecond. So we turn a 1 microsecond pulse of 100 millivolts per centimeter. And we did it at varying times in the plasma. So if you follow along here, we're going up. And then at this point here, which is 30 microseconds from the formation, I just turn on that 1 microsecond pulse. And look at what happens to the dribbling out electrons. They just turn off completely. And it sits there for something like 20 or 30 microseconds, and it very sharply turns back on. And then if you keep following it, it becomes virtually indistinguishable from the plasma to start with. And as you do this at different times, you can get very different information. Now, I'm just throwing this out as kind of a tease. I don't have anything substantive to say about it, other than I think there's the potential for some very interesting kind of quasi-equilibrium, non-equilibrium physics here associated with the evaporation going through this. And if we knew how to interpret this data, we could take tons of data that would do this for you. But obviously, there's some interesting dynamics going on here. Okay, I mentioned the plasma is expanding during that time. That expansion is driven by electron pressure. So even if I make a 1 Kelvin cloud of electrons, they really want to blow apart in nanoseconds. What's preventing them from doing that is the ions. So the electrons are exerting an outward pressure on the ions. And what you find is an expansion velocity that's the square root of kT electron over mass ion, which typically for our plasmas is kind of the 50 to 100 meter per second expansion velocity. Now what this means is the electrons must be doing work on the ions. And so that means there should be adiabatic cooling going on for the electrons. So if we're interested in the electron temperature of these plasmas as a function of time, there's a lot of processes that can go on. So I just said adiabatic cooling. The electrons are going to essentially try to give up all their energy to the ions. We saw the electrons are dribbling out, so there must be evaporative cooling going on as well. But since we don't really understand that process, it's hard to estimate that. There's something called disorder-induced heating, which basically I won't go into, but that's some initial heating right at the beginning of the plasma. And what I'm going to concentrate on is basically the 3-body recombination heating, and also electron Rydberg collisions. So basically, when I have a 3-body collision, 2 electrons and an ion, when the one electron gets bound, to conserve energy and momentum, the other electron gains that binding energy. So that's a source of heat, and that turns out to be a rather important source of heat. So if you want to measure electron temperature, it's rather challenging in these plasmas. You can't use traditional plasma physics techniques. We've only got 1 million ions sitting in the middle of our high vacuum chamber there. We did an early measurement a number of years ago where we essentially looked at that evaporation and would just apply a small change in the field to tip it and look at the particles dribbling out. That's a very tough thing to do. You're also sensitive to whether it's really a Boltzmann distribution or not. So, I mean, it worked to some extent, but we had kind of factor of 2 uncertainties, and it only worked in a limited early range of the plasma. So what we've gone to instead is using temperature-dependent plasma effects to get there. And the thing in the plasmas that have the strongest temperature dependence is three-body recombination. And there's this nice argument from Tom O'Neill. So three-body recombination goes as temperature to the -9/2, which is one of the strongest powers I know of for these kinds of things. You can understand it as from a simple argument, namely the frequency of an electron-ion collision is electron density times some cross-section, where we'll just throw in the Thomson radius, times the velocity. Now it's a three-body collision, so we need to add the third body. So just figure out the probability of there being a second electron nearby. Well, that's just electron density times my Thomson radius cubed. So the total collision rate, which is the product of these two, just goes in the end as t to the -9/2. And so this has a very strong inverse temperature dependence. And so whenever you get Rydbergs, you also get heating, as I mentioned. And the colder I make the sample, the more important this becomes. And the sort of seminal paper on this was Mansbeck and Keck, which did a very good Monte Carlo calculation back in 1968, which calculated essentially what the constant is out front of this three-body rate. And so if you go through this, basically you have a three-body rate, or Rydberg atom production, because you're typically going to form a few kT below the ionization limit. So for our plasmas in the tens of Kelvin range, this is going to be pretty high Rydberg atoms. So there's some three-body rate constant. This comes out of Mansbeck and Keck, and then an integral over the square of the electron density times the ion density. And so there's a lot that actually goes into this, because when you form a Rydberg atom, it's sitting there in a bath of other electrons, and so it can undergo electron-Rydberg collisions, and a lot of things can happen to that Rydberg atom. It can get driven to lower principal quantum number. It can get driven to higher principal quantum number. It can get reionized, and so you sort of get this soup. And then in addition, you've got radiative decay transitions. You also have blackbody going on. So in the end, the way this Mansbeck and Keck kind of formulation works is you set up a Monte Carlo calculation with all these rates in it that allows all these processes to go on and run through this soup. And when you really get recombination, it's when the principal quantum number has got low enough that radiation takes over, and then you can get a photon emitted, and then it goes down and really forms an atom. And so this just gives some of the various collision rates here. It's the radiative decay and blackbody transitions, and these are some of the electron-Rydberg collisions, one going up, which seems to have vanished, and one going down. So you can do, now of course, that was 1968 Monte Carlo. Now my grad student can just take a PC and do Monte Carlo and sort of repeat the thing, and it becomes trivial. And here just shows some Rydberg distribution for some set of, I don't even remember the initial parameters here. So if you want to look at this three-body recombination, you want to detect the Rydberg atoms. So there are a couple of ways you can do it. One is you can just field ionize, the traditional way of detecting Rydberg atoms. That destroys the plasma. It also has the problem that Rydberg atoms live for a long time. And so if I create my plasma, wait 20 microseconds, and field ionize, I'll tell you how many Rydberg atoms were there, but some of those were made 100 nanoseconds earlier, some were made 10 microseconds earlier and have undergone lots of collisions. So you get a sort of an integrated history. It gets very messy. Or you can also do microwave ionization, which basically requires the same size electric fields. It's a non-resonant process the way we do it, 2.5 gigahertz. And the nice thing is you can microwave ionize the Rydberg atoms, and the plasma is still there, so you can go in later and probe again if you'd like. Because if you do a short enough microwave pulse, you don't really do much in the way of affecting the plasma. The electrons have just quivered a little bit at 2.5 gigahertz and then stop. Eventually, you pump heat into the system, but if you do a short enough pulse, it's fine. So just to show you what CW microwaves do, so this shows that it has an effect. So basically here again is the black curve for a 3 Kelvin plasma with no microwaves. And then these two curves are basically just the difference between the black curve and the signal you get with the CW microwaves being on all the time. And you see you can get very dramatic differences. Again, this isn't necessarily that useful because you're integrating over all the dynamics of the plasma. here's a case where we just do a pulsed microwave ionization. So we put on, in this case, a 1 microsecond pulse and look at the number of Rydbergs coming out as the plasma varies. And you get actually what rather strange behavior. We saw this when the first time we did this with field ionization as well, is that you can actually get the Rydbergs to go up and come down and come back up here. And this is related to the complicated dynamics of where the principal quantum numbers are and how things are drifting up and down here. For this particular size of microwave field, basically we could microwave ionize things with principal quantum number above n equals 34. So this way of doing things, again, doesn't really give you very much information because it's got this integrated history. So what we'd really like to do is measure a three-body recombination. We want to know the sort of instantaneous rate. And so to do that, what we do is we go to a two-pulse system. So the basic idea is you put on that first microwave pulse, and that essentially field ionizes all the Rydberg states above some principal quantum number. And then we wait some short period of time. Three-body recombination goes on, collisions go on, and I'll repopulate some of those principal quantum numbers, and then I'll go and measure the number of Rydberg atoms created there. And this gives us closer, at least, to a instantaneous measurement of the Rydberg formation rate. And here's just an example of the data where we have two pulses, 200 nanoseconds of microwaves. We wait some time and then do it again. So I get microwave ionization of the Rydberg atoms, it refills, and then I get another pulse here. And what you see already is this is probably 5 microseconds or something, and it refills very quickly. That peak is almost the same size as that peak. So one of the challenges of doing this is that the recombination rates are so high that you can't wait very long between these things to see what's going on. And so what we basically do is we vary the time between the two pulses and figure out the number of Rydbergs coming in that second pulse, and then we can extrapolate. And when we do that, we get what we call a Rydberg refill rate. So again, this is for about n equals 35 and up. This is the number of Rydberg atoms that got created after I first stripped out everything from n equals 35 on up, trying to extrapolate down to sort of instantaneous time. And so what you see is this is time after creating the plasma, and the rate is quite large. That's 10 to the 8th per second. So we're up at about 10 to the 9th per second. So that's a pretty high overall rate. The other thing to notice is it hardly changes over this whole time, maybe a factor of 2 at most here. Now the density of the plasma from 10 microseconds out to 60 microseconds, it's probably down by 2 to 3 orders of magnitude in density. And remember, the three-body recombination rate goes as density squared, so that density squared term is down by 5 or 6 orders of magnitude, yet the Rydberg rate is roughly constant. So that must tell you that the temperature must be going down in concert such that it keeps the overall n squared t to the minus 9 halves expression about constant. So we did this to measure the three-body recombination rate, and we thought that we would be able to sort of update an experimental measurement of this kind of Mansbeck and Keck number. No one has ever looked at three-body recombination experimentally at these low temperatures. The problem is, unless you know your temperature very well, because of that t to the minus 9 halves term, you get a very large uncertainty in the three-body rate. So about the best we could do is sort of an order of magnitude estimate, because we don't really have a very good measurement of the electron temperature. And within that order of magnitude, it agreed with Mansbeck and Keck. Well, we looked at this, and here's a problem, so let's turn a problem into a feature. So we just instead say, okay, let's assume we know this three-body recombination coefficient and extract the temperature from the measured rate. So essentially just invert this equation. And the advantage to that is now my t to the minus 9 halves. That 9 halves power is now 2/9 power, and on the three-body rate. So even if that rate constant isn't that well known, it doesn't have much influence on my temperature because it only comes in as the 2/9 power. So now I've turned it into something that helps a lot. So with this, we we extracted the temperature as a function of time by monitoring the Rydberg rate. And up here, which you can barely see, was our original temperature measurements done where we tipped the distribution and looked at the electrons coming out from the tail of the distribution. And for technical reasons, that only worked very early in the plasma. And then here's our work here, and this is a model that Francis had done, actually well before we did our data here. So he should be given some kudos for that, because it agrees pretty well here. And so basically what you're seeing is that the electron temperature starts up in the tens of Kelvin regime, and then it cools down to below, actually if we go out to the full lifetime of plasma, down to the hundreds of millikelvin regime. Now this is rather substantial cooling, and it's presumably due to adiabatic cooling and evaporative cooling. But if it weren't for the three-body recombination heating, this would be down in the millikelvin temperature range if you just looked at adiabatic cooling by itself. So in fact, this temperature profile here is very much dominated actually by the collisions due to the three-body recombination. So one of the things you might think about is the plasma strongly coupled? That first ubiquitous plasma diagram showed the region where you reach strong coupling. To remind you, strong coupling is when you compare the energy associated with the Coulomb energy in a plasma compared to the kT. And so once the Coulomb energy is greater than kT, then you start getting correlations important. You can get liquid-like behavior. If you get strongly coupled enough, you can actually get crystalline-like behavior. So we can easily understand what the strong coupling parameter is. And remember, the Rydbergs produced roughly was a constant within a factor of 2. So I can just make the approximation that n squared times t to the minus 9/2 is a constant. And I also know just from my expansion measurements that the density goes down as t to the minus 3. So that tells me the temperature should be going as t to the minus 4/3. And if I plotted that on here, it would look in reasonable agreement with that. And what that tells you then is that the Coulomb coupling constant goes as t to the 1/3. So it's actually increasing. So it is becoming closer to strong coupling. However, for all the parameters we've investigated for the electrons, we start, because of disordered induced heating among other things, below 1, so down at about 0.13, and it maybe goes up by a factor of 2 up to about 0.2 here. So it looks like even with this substantial cooling, we don't get into the strong coupling regime because the density is decreasing as well. I would point out that if we were getting to strong coupling, then that three-body recombination theory wouldn't be correct anyway. So then we'd have some inconsistency. So this also shows that we're sort of in a self-consistent way to extract the temperature. I should point out that there's been recent work from one of our organizers and some of our other speakers that they went back to the Mansbeck and Keck and did a much better job. And basically, they got things that agreed fairly well with their experiment. The one thing I will point out is the real dramatic difference. This is energy changing collisions as a function of the change in energy here. And the big difference is between the Mansbeck and Keck, which basically kind of truncated things at small energy change. And the new Monte Carlo calculations have much higher low energy collisions. And so this was published last year. I will point out that one of the rather dramatic differences is if you look at the Rydberg distributions predicted, Mansbeck and Keck actually predicted a n to the 6th dependence in the Rydberg distribution, where this work produces n to the 4th scaling. But they both still give that t to the minus 9/2 dependence. Now, we've been working at various times. We've got sidetracked, so I don't have any data to show you here, trying to look at this n distribution. So basically, it gets a little more challenging because you have to do sort of a differential measurement. So I don't really have any data to show you here. We've had some preliminary data that kind of gave n to the 5th, but it had at least an uncertainty of 1. And it's like doing astrophysics, you know. So we don't really have anything that I want to say about that. So other than it's a bit of a challenging measurement because now I have to look at differential things to get the n distribution. So we're trying to do field ionization. So the first pulse we microwave ionize, the second pulse field ionize, and then hope to get the principal quantum number distribution out all in one shot. But so far that still hasn't fully worked. One comment I just wanted to make about starting with a gas of cold Rydberg atoms forming a plasma, you can ask, what's the temperature that I'm going to get? Because if I start with a laser tuned above the ionization limit, I know how much energy I put into the system. And so I kind of know what's available, and I can figure out how to get a temperature out. With the Rydberg atoms, I'm starting with a system that's overall bound, right? I'm creating atoms that are still have a negative binding energy. So what determines the temperature? Well, I don't know the answer to that. And boy, you really can't see this, so ignore that there. But this is for a 3 Kelvin plasma, Rydberg gas starting at n equals 130 or n equals 90. And what you can't see here is this is temperature versus time, but all 3 curves are exactly on top of one another. So just, I don't know what actually creates the electron temperature, but in a sense being above or below the ionization limit by a few Kelvin doesn't really matter whatsoever. So the temperature is determined presumably very quickly by the plasma dynamics going on. Okay, I wanted to connect to antihydrogen, and you'll hear from Jerry later in the session. And so, you know, he's going to talk about their ATRAP collaboration. Since he's here, I can make fun of him. So I want to point out the new elementary particle there. This is taken out of Jerry's paper. So these are electrons. So basically, no comment from the back there, I see. The basic idea and why there's this connection is that you want to form antihydrogen in these nested penning traps where you've got essentially an ultracold plasma of antiprotons and positrons. And if you look at the densities and temperatures, they're actually very similar to our work. The big difference is they tend to work in Tesla fields. So that changes the collisional dynamics. Now, as I'm sure you'll hear, that they have seen antihydrogen production, and there's plenty of evidence that says they're forming it in high Rydberg states. But for the interesting physics that you really hope to do with antihydrogen, you'd really like it down into the ground state. So understanding the dynamics and the mechanics of this 3-body recombination process and how you can drive population down to the ground state is actually very relevant to those things. So in our particular case, we're interested in extending our plasma lifetime, and we'd like to do it by adding magnetic fields. We're not going to go to Tesla fields. Because our electrons are so cold, we can put on a few Gauss field, and a Larmor radius of a cold electron is still tens of microns. And so the electrons can now get bound to the field lines, and now my ions, I sort of role reverse, and the ions are now bound to the electrons. How much longer do I have?
About 5 minutes.
Okay, that's fine. So in the case in the free expansion, essentially the electrons are bound to the heavy ions, and that keeps it as a neutral plasma that expands. If I apply a magnetic field now, in a sense, the ions should get bound to the electrons. And we can do that, we can understand that by doing our ion imaging. So basically, we create the plasma, let it evolve, and then apply a very large electric field to just slam the ion distribution onto our channel plate and then take images of it with a phosphor screen. And actually what you see is early on, you see rather interesting distributions. This is actually Coulomb explosion of the ion cloud as its time of flight going to the detector. It takes about 8 microseconds because it's coming from a very dense plasma, so there's a lot of Coulomb energy. If you wait long enough, the plasma has gotten big enough that the Coulomb explosion problem has gone away. And this is actually very similar to work we heard about yesterday from Jim, where he was talking about 2 ions at a time. We're talking about thousands of ions at a time. So what you see is the Coulomb explosion problem is going away, and then eventually you start to see the expansion of the plasma here. And that's with no magnetic field. If I add magnetic field, so then again, that's no magnetic field, you get something like this. And here's the expansion of the plasma in a 50 Gauss field. And you see that you can dramatically reduce the expansion because the electrons are bound to the field lines. The ions are then bound to the electrons. And this is just showing the increase of the plasma. If you look at the scaling versus magnetic field, it turns out to go as b to the minus 1/2. And it's a little bit of a subtle thing. What goes on whenever you have a plasma with particles of both signs or opposite signs, you can get an electron and an ion kind of hang around together for a little while. While they're hanging around together, they look kind of neutral, so they can drift along the field line, and then they break up again. And that in plasma physics is called ambipolar diffusion. So you do expect some diffusion. And this is a fit to a model of ambipolar diffusion. It turned out to be a little more complicated because you have to put in the temperature dynamics and the density dynamics while you're doing that. We've recently gone to applying fairly large magnetic fields transverse to our system. Before, I was imaging along the magnetic field, so I just had information on the radial. I couldn't tell you what it was doing along the magnetic field. Now, by applying the magnetic field sideways, we can actually see expansion now in both directions here. So this direction is along the magnetic field, and this is perpendicular to the magnetic field. So where we want to go with this is eventually to do a 3D confinement magnetic bottle geometry. We're still under design. We keep coming up with more things that we're trying, so we haven't quite started constructing yet. But we have figured out how to apply up to 500 Gauss fields to our plasmas in the time necessary to do the experiment, so that should work just fine. And I just wanted to end showing you that these really are plasmas. This was data in the process of doing that, applying the magnetic fields. We had to do some optical pumping. So this is plasma instabilities that just were kind of a fluke that we found by applying very weak electric fields crossed with a weak magnetic field. So for instance, 2 Gauss crossed with a 10 millivolt per centimeter electric field, and you get these spiking electron distributions coming out, which is a signature of a plasma instability. So it's real plasma physics. So let me just say, you know, one of the things we're interested in still is ways to make the electrons strongly coupled. This disorder-induced heating I alluded to, perhaps we can build in correlations by starting with an optical lattice. I'm interested in whether we can sort of use the microwaves in some clever way to kind of dress the system so that when it undergoes these collisions, I get different couplings between the principal quantum numbers. And actually adding magnetic confinement is going to modify the expansion dynamics. That actually will probably go in the opposite direction because now I won't get the adiabatic cooling. And the other thing is we can investigate evaporative cooling to see if applying small electric fields actually can give increased cooling. So let me just end by saying this is my current group at the moment, actually 1 graduate student and 1 undergraduate working on this experiment. Thanks.
So in your technique where you ionize your plasma with microwaves, is the frequency of microwaves above or below the plasma frequency? And is that relevant at all?
It's way above the plasma frequency.
Okay.
So I believe the only thing the microwaves do is the electrons quiver at 2.5 gigahertz in this case. And we see if we leave on a long pulse, it starts to heat the plasma because presumably as they're doing this, they start colliding and generating heat. So part of, not only is do we go short because the recombination time is rapid, but also we want to go as short as we can so that we don't pump heat into the plasma.
Yeah. That's nice, Steve. I was wondering about the case where you're getting rid of the Rydberg atoms above n equals 5. And then I guess your assumption was that you're repopulating them all from weaker binding. But can't also the more deeply bound atoms, electrons in the more deeply bound atoms, diffuse to larger energy through collisions as well as you said, particles actually go to larger energy as well as to lower?
Yes, no, you're right. There is some of that going on, but I think if you look at the rates, I mean, that's probably at the 10 or 20% level, just because the rates are higher for the higher up stuff there.
It's true that particles at deep binding tend to go to lower energy than
higher going to higher energy.
It's actually surprisingly broad.
Yes, no, you're right. It is. So there's actually very little, not that much difference between going up and going down. It just kind of diffuses. I agree.
From the shape of that refilling curve as a function of time, is there potential to say anything from it about the dynamics and how it saturates and look at the time dependence? I wouldn't expect it to be linear over the whole thing. It should.
No, it will kind of saturate. Yeah. I don't know. I mean, the real challenge is that refilling rate is so high that you know, it's really up at 10 to the 8th to 10 to the 9th per second. So you have to do things at very short times. And so very quickly we find that, you know, you're not really gaining any new information, I think, later on, because you've kind of come back to the whatever the state is. I guess another way of saying it is, I think, coming back to Dan's comments too, is that if I presume if I tried this, I haven't tried this, if I did a Monte Carlo simulation and I made that big cut, it would go back to its kind of quasi-equilibrium state very rapidly in of order a microsecond or so, just because the rates are so large.
One last question.
What fraction of the atoms are ionized initially?
Oh, so when we make these plasmas, we typically ionize around 30%. If we work hard, we can do 50%. There's always the question is, what about the leftover neutral atoms sitting there? Is there any interactions there? If you estimate the collision cross-sections, it seems unlikely. The one other thing we did long time ago was, I didn't really talk about this, but we create our plasma from metastable xenon. So the atoms that are hanging around are in the metastable state, 8 eV above the ionization limit. So we actually checked that we have a way that we could dump all the metastable atoms to ground state xenon, and that made no difference. So I would tend to argue if being metastable or not didn't have an effect, then probably neutrals aren't having an effect at all.
Okay, let's thank Steve again.